Thank you for joining me in this configuration section. I hope you enjoyed the previous video. Here, I'll show you how the inter-AS option B is configured on the ASBR as we have them in this design. We have the route reflector, which is responsible for propagating routes to R3. R3 in this case is the PE. R4 is acting as the PE and an ASBR in this scenario. And as the PE, it connects to R14, which serves as a backup path for the campus network, which is assigned to the VRF shown. In R4 and R9, they are acting as a backup path for the other inter-AS between R1 and R10. R11 in this case is a route reflector that is responsible for the reflection of route between the two routers R9 and R10. At the same time, it is a PE to R12, which then is responsible for the propagation of the LAN IP prefix from the remote. Now we go to R3. You can see there are only two VRFs that are configured, and that is the RD, and it has been configured into the assigned interface. IP address is a /30, as we see. It already has formed a BGP session with R2. R2 in this case is a route reflector. We can see here that R2 has already established sessions with the three routers. Similarly, R1 has formed adjacency with R2 and also learned some prefixes. That prefix is to another AS that was shown in the previous video of inter-AS option A. Please click in the description to see more details about that. Similarly, on R4, we have this converged as well, but there is no route that is learned here in this BGP address family. However, in the VPN v4, we are learning the prefixes as intended. You see these IP prefixes are to inter-AS1 because they are not reflecting in the design, so it is not needed. We only need R2 in this case. R9 on the other hand has not been configured with any BGP configuration. We only have this pre-configuration, which is incomplete. Currently, the inter-AS link is yet to be configured, but we have the internal gateway protocol, that is ISIS, already converged within the service provider, SP3 in this case. And you see also it is learning the routes that are required. It has learned also from R11, which is going to act as our route reflector. Similarly, on R10, there is no VRF required on this ASBR router. We have the basic IP configurations, but we do not have the inter-AS link configured yet. Also, we have the ISIS configured and converged, also learning the R11 prefix. And on R11, we have the configuration of the VRF assigned to it, but there is no BGP configured yet. I deliberately left that in order for us to do that together. Here, I'm just showing you the direct connection between R11 and its peers. The configuration is just basic. The interface already assigned to the VRF, and we also have ISIS running, but there is no BGP between R11 and R12 yet. That will be configured in a couple of seconds. So we see this IP address is already learned by the two ASBRs, and it means that they will be able to reach through and form adjacency when we are ready to configure that. Reachability between R11 and R12 exists, and that is on a /31 address. It doesn't matter the subnet mask that you're using, particularly for the WAN, you can use the /31 or /30. It depends on what is available to you at that time. You can conserve some IP addresses in the /31. On the R12, you do not need the VRF except you are implementing VRF Lite based on the conditions that are provided by the customer. And remember, the business requirement supersedes your design inspirations or factors because the design is subject to the business requirement. So we don't need VRF Lite in this case on R12, hence we will continue. For now, we have BGP configuration basic on R12, but R11 needs to form adjacency on BGP. So we will go ahead to configure R11 to form BGP adjacency with R12. So at least we can learn what R12 knows about. In this case, it will be just one prefix, which is the LAN IP. Here we are learning already from R12 because the adjacency has just formed. But R12 is not learning yet from R11 because there is nothing coming from the service provider 1 in our case. So we quickly have to configure the inter-AS link. On R1, the inter-AS link is being configured with an IP address 110.0.0.1. It's a /30 address. Then we can mirror the same configuration on R10, R4, and R9. Here on R10, we do the same config just to verify first. That is our interface that will act as the inter-AS link interface. And we can check if there is anything existing yet. There is nothing. It's a shutdown. It's only a description. And we configure the IP address .2, in this case /30. Then we go to R4, checking the interface also in this case if there is anything pre-existing, or IP address also in this case is a /30 address, which is the 49.0.0.1/30. We activate the interface. We have to activate all interfaces after the configuration had been done. Then mirror the same IP on R9, in this case the .2/30. Then we activate as well. Now we have IP connectivity between R9 and R4. Now we have to configure BGP between the ASBR. We're starting with R1 in this case, and that is why I have it pairing with .2, which is in another AS, giving it a description. And now we go into the address family, the VPN v4. This is where we have the MP-BGP, that is the multi-protocol BGP. We activate it and also send the community, in this case both, which is the standard and extended. You can verify, so that we can copy out this configuration and modify it, apply it to other ASBRs. We only need the multi-protocol section part, which is the VPN v4 and the basic BGP configuration. So we edit the peer IP in this case, and you have to also put into consideration the AS number. You have to use the appropriate one. We change all that needs to be modified. Copy that and then we'll paste that on R10 in this case, so that we can form the adjacency over the inter-AS link between R1 and R10. Now we have that formed, and you notice that MPLS BGP forwarding is activated automatically on the inter-AS link. This is a feature that allows the ASBR to forward labeled MPLS packet over the MP-BGP. This is one of the reasons why you do not need to run LDP directly on the inter-AS link, because it would perform the forwarding of labeled prefix. Once you disable this feature, it makes the ASBR to drop any labeled packet that it finds in that segment. So always ensure that you have it activated when you're operating option B. We edit also and copy the config, go to R9 in this case, paste it, go to R4 now and check. Now we are learning some prefixes in the VPN v4 address family. We need to disable the ARF feature. Remember, this is very important. We replicate same on other ASBRs. It has been done on R1 earlier, so there is no need to do that again. We see here R1 is learning from 2 but nothing from R10. Similarly, R4 is not learning from R9 but is learning from other IBGPs. And R9 is not learning anything yet from R4, same as R10. Now we have to configure the peering between R10 and R11. Remember that R11 is a route reflector, and so we can configure that to at least make R9 and R10 know about the remote LAN prefix, which is already being learned by R11 in that VRF. You need to specify next up self when configuring the address family with the route reflector, which is instructing the ASBR to rewrite the next up address with its own local address that is known to the route reflector. Very important, the next up self needs to be specified in order to configure this option B using next up self. We can copy this configuration, modify this configuration to suit R9, then we copy and paste, and we have to do the same on R11 in order to be able to form adjacency with both R9 and R10. So similarly, R11 will take a similar config, but a config that suits it. And now we paste the configuration on R11 in order to form adjacency with R9 and R10. Remember, R11 is a route reflector, so we should expect to see it pairing with 3 pairs, R9, R10, and R12. For now, it is not learning any prefix over the MP-BGP session to R9 and R10, but we can see it's learning from R12. So on 9, you can verify we are learning that prefix that is coming from the remote through R11. Similarly, R10 is expected to see same. So we have a one-way propagation which is coming from the remote. Also, we can see here that route has been advertised over the inter-AS link in one direction. But can we see it on the PE yet? PE is learning from the CE over the IP address that we have on R3. Still, there is nothing coming back from SP1 towards SP3. The PE is learning from the CE. Now, on the route reflector in SP1, we can see that the route reflector is learning 12 routes from the PE, which is router 3 in this case. And we will see them being separated by the RD. You can see there are 3 RDs, which are the 3 VRF tables on the route reflector in service provider 1. But it is not being reflected on the ASBR. That is, the prefixes learned from R3 are not sent to the ASBR1. And that means we need to disable the automatic route filtering feature on the route reflector in order to achieve this. Once you do that, you can refresh, do a soft route refresh and verify again. Now we can see that those prefixes are now being learned because we have disabled the ARF on the route reflector. The similar thing is happening on R4. And now we are learning those prefixes over the inter-AS link, even in SP3 in this case. R10 is learning the reflected routes as well. R11, as at that time it wasn't learning, but now it is now learning those prefixes, both the reflected prefix and the one that is coming directly from the inter-AS peer. But R12 is not learning yet. So remember that I mentioned to you that you need to import VRF that is coming from the foreign AS into the local VRF of the local service provider. And in that case, we need to import the VRF that is taking care of the foreign prefixes, which in this case is 15,67717. And that is our local VRF below. And you see that this VRFs has not been injected into our local VRF. And so we need to inject the foreign VRF into the local VRF simply by going into the VRF and import the route target for the foreign routes. With this command, you can see that the prefixes that are coming from the campus side will then be learned by the remote router, which is R12 in this case. When you refresh routes and we go back to R12 again, we can see that the PE is advertising these prefixes towards R12, and R12 for sure is expected to be learning these prefixes as seen. To verify this, you can check the BGP table and you will see that they are coming from the remote campus site. There we'll see also that R9 already has rewritten the next stop address, which is very important in option B using the next stop method. So looking into the VPN v4 table, the MP-BGP table, we have two available paths to reach that particular prefix, which is coming from the foreign VRF, and this is the path that is learned via R10, which is the ASBR10, and this is the reflected route also, which is coming over R9, and this is the best path. Now here we have on the lower part, there is only one available path in the local VRF, and that is the one that was injected from the foreign VRF. As you can see here, you have this to be injected from R9 into the local VRF on R11 being the PE, and you can see that there is an identifier that specifies the foreign VRF. Also, we have this to be labeled route, and this is exactly what this solution is about. Similarly, on R3 being the PE in SP1, we need to do the route importation into the VRF. It has not been done yet, and that is the reason we are not able to see 192.168.20.0, because that is a foreign prefix coming from a foreign VRF. And in some situations where you do not need to do this importation of VRF entries, you could consider a rewrite option of the extended community at the ASBR level. I explained this in the presentation video. Please check the description section to see that video. I'm still going to make a video that shows exactly how that works. So for the purpose of this case, we need to import the foreign VRF into the local VRF, and that is simply by importing the route target. Now we can see the remote LAN prefix in the local VRF table of the service provider 1 PE. Verify that. You can check specifically in that VRF table and you can see it's been rewritten already. At this point, reachability between the campus and the remote site should be achievable because we now see the prefixes being learned, and that is all that is required. Remember, when you are dealing with this kind of situation where you have to import VRF, be careful in the production environment because you might need to filter some prefixes, especially when you are dealing with cases where you are dealing with too many routes. So here, running pings and traceroute shows you reachability condition. We can see here that traffic going from the campus towards the remote, that is from R13 to R12, we are simulating a LAN-to-LAN communication. That is why I have it sourced from local LAN IP address. And in the traceroute, we can see here that the traffic prefers to go through the inter-AS link between R1 and R10. Now we can check also how the traffic is flowing back from the remote to the campus. So the servers behind the R13 are going through that path, and that is exactly where the traffic is taken. What about going back from the remote towards the campus? So here, ping 192.168.10.1, sourcing it from the LAN IP. Now we have reachability. We can do the trace to see how it is flowing. So you see there, it is going through R4, which is a typical example of an asymmetric routing. Please ignore the latency values. It's because of the background processes I'm running. So let's ignore the latency values for now. In order to solve this asymmetric problem, we can perform traffic engineering using the path attributes of BGP and applying it to the MP-BGP peer. So in this case, I'm making use of the simple ones that are local preference and AS path and the metric. I'm using the local preference to influence the traffic flowing outbound of service provider 1, and also the AS path and metric to influence how service provider 3 will get traffic into the service provider 1. So in order to get more details on BGP path attributes, you can pick up BGP documentations and just go through each of those path attributes. Now we can apply these route maps in the appropriate directions. Backup in is applied in the outbound direction and backup out in the inbound direction. This is to influence how the peers in each of those directions will react and behave towards that service provider network. With this, we can go back to R12 and see how the traffic will flow. Now that we have influenced the traffic flow, we can see in the BGP table on R4 that the local preference of the LAN from the remote has now been decremented to 50 as specified. And so when this traffic is flowing out of this AS, it will go through R1 as expected. And the same thing happened to R9, which is SP3. In this case, the AS path has been influenced. The metric also has been influenced. And we can see that it is preferring to go through R10 in order to reach the prefixes coming from R13. So this still didn't change because it was the preferred path. However, in this case, going back to the campus from the remote has now preferred the inter-AS between R1 and R10 as seen. That is exactly what we need to do in order to achieve the symmetric routing. Thank you for watching this video. We have just completed the implementation of inter-AS MPLS VPN option B using the next up self method. I hope you found this helpful, and I look forward to making more videos for you. You can pause the video, take it back, lab it, do any form of practices that you can using this video. And in fact, I deliberately did not show the configuration of R4 towards R14. I would like you to try this and give a like if you are able to achieve reachability between R14 and R12. Please ask questions if you have any, and I look forward to making other videos. Thank you. Like, share, comment, please subscribe. Until I come your way again. Bye for now.